we can start with introduction. So for me, it's really a pleasure to introduce Ozge. She's an astonishing researcher, but also she's a very, very good friend of mine. So she's coming to visit us, and we took the opportunity to invite her to give a talk about her research. So I just wanted to describe a little bit her bio, because also it's amazing that she has different heads. So actually she's a faculty member of Sabanci University since 2012. So it means that she's teaching at a few hours per semester, or quite a few hours. 42 hours. So, and also she will explain us her research that is mainly now related to silicon-based composites and additives and subtractive manufacturing of ceramics. Her background, she did a PhD at Material Science Engineering at Sabanci University in 2004. And then she moved to Massachusetts Institute, MIT, in 2009, where she actually focused on cost-effective fabrication of biomolecular devices and surface sciences. And then another postdoctoral fellowship at Harvard University, where she developed tools and techniques for resource-limiting settings. But this is about her research, but it's not only that. Actually, she's an entrepreneur. She has founded, she's co-founder and CEO of Surgitate, that I asked her to actually introduce this company to us at the end of her talk, where they fabricate, designs and fabricates tactile surgical training platforms since 2014. So it's one of the leading companies in the world about that topic. She will explain us later about that. And since 2 years ago, officially last year, but actually she's Chief of Science Officer of Park Labs. That is an innovation and transformation hub in the entrepreneurship ecosystem in Turkey. So as you can see, it's a possibility that you can do anything you want, so you just need to spend time. And she has what she says, different heads, so in faculty member, research, and also entrepreneurship, and I think she's an excellent role model. So the floor is yours. Thanks, Ozge.
Anna, that you really raised the expectation, I believe. Wonderful. Well, thank you very much for the introduction and the kind words. I'm very happy to be here. So today, let me start with colloidal science. Let me start with ceramics, actually. So let me show you these videos first, then you will understand what you are looking at. So these are those of advanced ceramics. You are looking of yttria stabilized zirconia here. And we can play with those things as if they are like a silly putty, or they are like, this Play-Doh. So, and throughout the talk, I will be talking about these advantages of using this type of rheology in the subtractive manufacturing of ceramics mostly. So as you might have seen on the right, we have bought all these tools from Amazon, and we actually shape these, let's say, putties or Play-Dohs through all this stuff, and then you can erase one pattern and introduce another one. I would like to draw your attention to this video at the moment. In that video, please look at the chip formation. So the chip formation in that video is like, it is long, as if you are cutting a metal rather than you are basically doing this manufacturing on a ceramic piece. So that part is actually something that I'm going to be talking on. And why did I get into this topic? Why are we basically doing this processing from this dough-like structure? So one of the things that we have been hearing in academia, also in industry, is Industry 4.0, Industry 4.0, and then we are now hearing Industry 5.0. I don't know if you are aware of it, but now there is an Industry 5.0. To be honest, I do find it a little bit of hype, but then, it is what it is, right? And then, what is Industry 4.0? We are really relying on collecting immense amounts of data on the equipment that basically shapes metals and plastics and ceramics. On the other hand, if you look at this Industry 4.0, metals and plastics, they are doing very well in terms of data collection and analyzing this data. On the other hand, the ceramics are not doing that well. They significantly lag behind for all these benefits of Industry 4.0 that could introduce to the manufacturing. Because the standardization in the ceramics is a challenge. So when you are shaping a metal or when you are actually molding a plastic part, you know what to expect. With ceramics, because of their brittle nature, they break, right? And most of the time we have huge amounts of materials leak. When I am talking to the established industry, they are really talking about 30% of their, the trash once they are actually talking about really ceramics manufacturing. And of course, the issue with the ceramics manufacturing, if you do this shaping after sintering, you are not, and then you are breaking stuff, you are not only losing the material, but you are also losing all the energy that you put into the stuff already. And that is a huge amount of energy, considering we are really talking about temperatures over 1500 Celsius and such, right? In order to sinter the ceramics. So my basic research question was like, do we have to do this way, right? So why are we processing ceramics and then with the techniques that are basically designed for metals? If you are talking about subtractive manufacturing, you are mostly talking about CNC and such, right? And these kind of machines, they are designed for metals. They are not designed with the thought of ceramics in mind. So we are really trying to adapt what is out there for the near net shaping of the ceramics. So, and then if you Google, right, one of the keywords of our times is actually custom-based manufacturing, right? People would like to have their own stuff in the shapes that they would like them and such. For if you Google custom-based manufacturing and ceramics, you will end up with tiles. So apparently you could choose the tile color and shape and such for your bathroom and kitchen. But then if you are really looking at the manufacturing of advanced ceramics in a customized way, like low number manufacturing, you wouldn't find much stuff, right? So this custom-based manufacturing in ceramics is a huge question mark. And why is it important? So with the corona and such, what we have learned is the digital companies, they made a lot of money because we shifted to these online systems pretty quickly. But at the same time, we have learned if you don't do materials and manufacturing, you might die, right? People were after ventilators, people were after personal protective equipment. So if you do not manufacture, then things are not going well for you. And then if you remember also, for all the seminars and conferences that we used to attend like 5-6 years ago, people were constantly talking about globalization and all these kind of things. Now everyone is talking about local production, right? So in essence, we need to devise those schemes, of course, economies of scale. If someone is producing an equipment for, 1 million times per year, it is fine. But then what if you need a piece easy to access and such, but you only need 500 of them? So what are we going to do? You need to do this CNC-based machining type of stuff, right? You need to have access to low number production and prototyping, especially for this a possible supply chain crisis, which we have experienced in the past couple of years. So we do manufacturing at green state. So the thing about green state manufacturing is, so green body of a ceramic is this loosely consolidated powder. And then if you machine that powder, you have access to, you can do this with lower amounts of forces, right? Think about a ceramic that is sintered already. Think about your mug that you drink coffee with. Of course, it's not an advanced ceramic, but then imagine that you are trying to shape that mug at this after sintering, right? The most likely result is the breaking of the piece itself. But then if you do the manufacturing at the green state, you can actually do these things with much lower forces. And of course, the added benefit is if you try to do this manufacturing at the sintered state, you're experiencing lots of tool wear, because cutting a very hard brittle ceramic with a soft tool wouldn't be possible. Even the hard tools, they experience the tool wear. So green machining is advantageous in terms of the tool wear and the amount of energy and force that you need to use. Of course, the disadvantage is it's going to shrink upon sintering, right? So it has to be predictable and such. So we know that that's why people are resorting to sintering, that machining at the sintered state, so that they know that they will have the dimensional stability. So what we do is green machining. And then I will elaborate on this. So what we do is what we do special is we prepare the green body to be machined. So all these Play-Dohs that you have seen in the first two slides are actually putties, let's say. You can put it into the CNC machine and then you can machine it, right? So that is what we are doing. We are doing the green body. So the novelty of this research is preparation of the green body, and what we can do with these basically malleable self-standing doors as opposed to what people are doing in the preparation of other types of green bodies. So let's see what people do. So there is actually isostatic pressing techniques. You use elastic molds and then you put this slurry of the ceramic into that mold. And then you basically isostatically pressure the system so that you get a compact in the end. That is one way. And then you also have, you can have pellets by compacting, again, like, pressurizing the pellets into, particles into each other through a powder compaction machine. And on the other hand, you could also do, you have your ceramic particles, right? And you would like to have a soft matrix in order for the green machining to work. So that is how green machining is, right? You have this thing you put into the CNC. So what people do is they create a matrix around those ceramic particles. So how do you create a matrix? You can either initiate a polymerization around those particles, and then you end up with a polymer ceramic composite, right? That is actually ceramic particles that are suspended in an organic matrix, right? So usually acrylamide is used in order to provide that kind of matrices, and that is a toxic monomer. And at the same time, sometimes they mix the polymer with they mix ceramic with a polymer so that they explore the rheological properties of the polymer rather than the ceramic itself. So these are all composite materials. There, I'm against calling these things basically just ceramics, right? Because actually what you are relying on is the properties of the polymer, not the properties of the ceramic. And most of the time you have to use copious amounts of matter with different types of matter, like, different types of chemicals, binders, dispersants, and these kind of things. And then, of course, the idea here with the organic matrix methods, you have to remove it afterwards, right? So the idea is, like, in sintering, we are trying to densify the structure by getting particles as close to each other, right? And then when you have lots of organic matrix around, you have to do a special burnout step to get rid of that matrix and such. So this is what is available. So what we do is, like, in 2021, we have come up with this concept of just this easy to implement green machinability to advanced ceramics. So, and the idea is, here we have these ceramic particles, and is it possible to basically induce homogeneous coagulation in colloidal systems? What do we mean by the homogeneous coagulation? I get into this business because I used to work on cement. So you might have colloidal particles, and you would like them to get attached to each other. You would like to have them to, because of this dough-like rheology, you would like to play with them, like be able to play with them. It is not a slip casting solution. Like, I don't know if you are familiar with this, but then if you have, for instance, alumina, you mix it with water, you have this alumina suspension, and that's a slip system, right? You basically pour it into a mold. Usually, like, that's how the toilets are being made. You have these structures, you have the toilet-shaped mold, gypsum mold, so that it allows the water to evaporate from the system. So that's a slip casting system. We don't want this. We want something that we can shape. Either we can push it into a mold, or we can directly put it into a machine. So it cannot flow. So that part is important, right? I am trying to make a system that doesn't flow, right? So, well, how can you create those systems if you coagulate the particles together but homogeneously, because otherwise the water will get out, and it's called bleeding. So you don't want some of the ceramics to come here and then you see water in the system. That is also a common problem in cement rheology. So what we have created is this is a polymer that has an ionic backbone. And with that ionic backbone, what we can do is cover these particles with a monolayer, and like if a single polymer is actually bridging among a couple of particles, then you see this homogeneous coagulation effect. And what we do in this paper and others is we modify the ionic behavior of the system. So how you modify the ionic behavior of the system is basically you introduce different types of monomers to modify polyacrylic acid. And then you create this adsorption behavior in this type of polymers. So what we do is to characterize the adsorption behavior of these systems, we do electrokinetic characterization. We measure the zeta potential of the systems. Ideally, the zeta potential values above 20 or minus 20 is actually indicating the stability in colloidal systems. So in here, for instance, like, and we have this, as you see, we have this different composition of polymers that we scan. So you can have the homopolymers of these monomers, or you can have the, copolymers with acrylic acid. And you can also modify the second monomer in order to obtain a different adsorption behavior. So that is what we do. We need to make sure that it is actually a stable solution. That's why we track the zeta potential. We also track the potential of those polymers to lower the zeta potential, right? Because you get more stability if you introduce more charge onto your system. And then we also track the hydrodynamic radius to see where we have access to the most adsorption, or the most stable structure and such. And we track the flock size as well, right? Because we really need to know the capacity of our polymer to bring those particles together. And you observe this through the formation of the flocks. And we do these experiments at the best polymer. We choose the best polymer that we would like to work with. And we constantly increase the amount of the particles in order to see the flock formation behavior. So in here, you see this AMPS 50 polymer, 50% acrylic acid, 50% AMPS is actually giving us the best behavior. So also, if you look at here, so in zeta potential, that polymer itself, this AMPS 51, 50% AMPS, 50% acrylic acid, it lowered the zeta potential better than the others. And in here, it managed to decrease the hydrodynamic radius better than others. So that is why we have chosen. Okay, I will insist. No, I'm just trying to shift to the next slide. I think, yes, here. If I am more insistent. Good. So we have chosen our polymer based on the electrokinetic studies. What we are trying in this slide is to find the minimum amount of polymer. Because like if I was telling you, when I was trashing other green body formation methods, I told you that, these guys are adding lots of material into their systems. And what we are trying to do also for these circular practices and the green, Green Deal EU is introducing, we are really trying to not to use materials if we don't need to. So in here, the idea is to figure out the smallest amount of polymer that we should be adding to the system in order to get this homogeneous coagulation behavior. So that is why we do rheology. And in here, so as you see, we are looking at the particles at 45 to 8%. And in here, we are having all these polymers that we work with, like that we would like to try. And in here, if you are around this range, you don't get a dough, you get an ink, which I will be talking about. So that like in order to get dough-like rheology, that you should be around here. And among those, we have chosen this AMPS 50. And in here, we are varying the amounts of AMPS 50. So again, we would like to be here, let's say in terms of the rheological response. If we basically do this at with the neat and 0.5%, we don't get the dough, but then we get the dough among here. So in order to get this work, we pick up the smallest amount of this additive introduction into the system at like 1 to 8%. Like this behavior is good for us. So we stick to the minimum amount of polymer that we are going to use and coagulate this system. So that is how we do that's where we use this rheological characterization. We also check the different amounts of molecular weights. It didn't make much difference. And then we also check the moisture content in order to understand why one polymer works better than the other. As you see, this AMPS-50 that is performing best in the electrokinetic characterization, it is also performing best in here in terms of keeping the moisture inside the system, so that it really keeps the system more malleable than the others. And what we do with this is here, like, left, up and down. This is laser machining, actually. This is a carbon dioxide laser, which we bought for $5,000 simply. And then we could actually shape these ceramic doughs by just cutting them. And then they cut like paper. You should see how it, how it happens. And you could create all these complex shapes. And this is a single pass. It is not that we cut it several times, it just cuts the system. And in here, you are seeing basic machining operations, and we can drill holes into this system. And the top is sintered, and the bottom is at the green state right after machining. We have this classical amounts of shrinkage in yttrium stabilized zirconia. So we could also, measure these forces. This is very interesting, right? I mean, look at this. You could cut a ceramic with only 3 Newton force. It's very good. Right, so it is as if you are touching the ceramic and then you are cutting it very nicely. So that is also important for the green practices, for the Green Deal, to be able to machine ceramics with minimum amount of power. Okay. So the other topic that I was talking about, this materials leakage problem. We could actually get 100%, but then these results are in preparation, so I didn't add them here. What you're looking at is, again, laser cutting, and then this is drilling. And then this is the system where you have this 40% addition of the recycling material into the system. Yes? No, please, let's do it more like this. I am curious about that. What is the scale here? So they are like the base of the containers. Like less than 2 millimeters. 2 millimeters, less than. The base of the exactly. So the entire thing is this much. So even. And have you tried to see what is the lowest feature you can form? True. So in here, what we have seen, we are bound by the spot size of the laser in the carbon dioxide. So I didn't add these things, but then I also have ND-YAG results. So we could also do surface structuring with ND-YAG and such. It is really, I think we can get like 500 micron in terms of really shaping a small. I think I have some interest in being able to cut small pieces of ceramic. Okay, good. Don't forget that there's thermal damage around the, I will show the laser machining of magnesium oxide. There is some thermal damage with the local sintering with the laser. No, but I did not. You can. But it's good. So I think 1 millimeter is easy for us. Let me put it that way. If it is a size scale that you are interested. Okay. So we could actually incorporate these intentionally broken parts into the system, but then I would like to give a disclaimer here. The added parts are coming from the machine stuff. So if you cannot recycle the laser cut stuff, but you can use other materials that are waste from machining and such into the laser system because of this partial sintering. Okay, and then many people who are trying to do this recycling of this type of materials, they do ball milling and then they do sonication and all these kind of things to incorporate this waste material into the system. We don't do anything, we just do mixing. We don't also do sieving and such. So again, this is in line with us trying to use minimum amount of energy in the processing of these materials. All right, so the next one. So this was yttrium stabilized zirconia. This is actually my most boring publication, I should say. because like, you need to parameterize stuff. And I think it is for us, it is parameterization of stuff. Because we are trying to convince the industry to adopt this type of green bodies in their use, right? And in order to do that, you need to parameterize the system and then convince the industry that this is a good, reliable method with everything. So that is what we have done. We really worked on the parameterization of this system. This time we have chosen an alumina dough. And why we have chosen alumina? Because it is the most frequently used advanced ceramic, right? So we wanted to show what we can do with alumina. And in here we did different types of machining on the system. Here, I would like to take a small break from these doughs. So from the beginning of this talk, I am talking about this dough structure. And you are now looking at a matrix. Here you see different amounts of ceramic particles that we add into the system. And in here, you are looking at the different amounts of the additive, the polymer that we design into the system. This is just water, additive, and ceramic particle, okay? So if you look at this, with the same type of polymer, right? You could get at different particle loadings. And if you look at here, 78 weight%, and then we have 1 weight% additive here, you get a very nice dough. But then if you start increasing the amount of the additive in the system, you end up with having an ink, because that polymer is behaving like a dispersant as well. So if you put so much in it, what you are going to have a system that flows. And if you would like to do the dough, you don't want the system to flow. So we stop here, right? And if you add so much materials into the system, then the amount of polymer is not enough for it to cover the ceramic particles. You end up with the surface cracks and such. So whenever we are choosing a system, we support ourselves with electrokinetic characterization and rheological characterization, but at the same time, this visual matrix. So I used to do this ceramic inks. I don't know if there is anyone who is doing robocasting or direct ink writing with ceramics here. But then the idea is to put as much as ceramic particles into the system, but it still flows as if that you are actually getting it out of a syringe or a toothpaste kind of idea, right? So the idea over there is to put as much as particles into the system, because once the filament is printed, you would like it to be robust, because now you need to introduce the second layer, third layer on top, so it should be able to carry the amount of weight of the consequent filaments in the system. So we were at those times designing these ceramic inks with lots of loading, such that we produce this nice filaments. And that is how we got into this dough business as well. So just to give you an idea, and so I used to do cement rheology, and with this cement rheology, it is interesting. Like these in 1990s, people have solved this colloidal suspension problem. What is the colloidal suspension problem? Is you would like a homogeneous suspension, right? If you are working with cement, you guys are seeing probably, well, we are in a civilized country, but maybe you don't. All these cement trucks, they are driving fast, right? And they are driving fast because from the first touch of water, the cement starts the phase transformation. And then until it gets to the point of delivery, the cement might be actually solid. So they don't want this. So in order to prevent it, they come up with this super plasticizers to modify the rheology of cement. And the idea is over there is introducing electrostatic repulsion as well as steric hindrance to sustain a stable suspension of ceramic cement particles, which are also ceramic particles themselves. So and then in 1990s they have solved the problem, saying that only ionic repulsion is not enough, but you have to also have this steric hindrance. 1990s. Ceramic inks nowadays, they only use electrostatic repulsion. I don't get this, but they do. They are using stuff like polyacrylic acid and such as the homopolymer form. They basically introduce the binders and such, and then they have good fibers, but then they are really ignoring the effect of steric hindrance for the, it is a power that we have in material science, but we don't use it. It is just interesting to me. So what we did in our previous work, we have worked on these colloidal systems to optimize is kind of maximized is the amount of particles that you can introduce to the system. And there are calculations that tell you, okay, this is the theoretical limit that you could have in a suspension. And here we are almost at the theoretical limit with alumina. This is, I think, 83% weight. And look at this. This is just 1%, 1.5% less. So if you really don't optimize, you cannot have this, towers of filaments that you could do. So, and then we optimize these systems by really working on the steric hindrance. We modified the side chains of a polymer, the density of the side chains and the length of the side chains in order to really reach the theoretical limits of these loadings. So, but inks are different, they flow. And in here, I am talking about the dose. Right. So again, boring stuff. You have to do different diameters of the tools. 1 millimeter tool, 2 millimeter tool. You basically check the surface profile. You try to get the surface as smooth as possible before and after sintering, and then you check your material removal rate and such. Again, it's not something that I'm super proud of, but it was needed to be done because, like, my aim for the rest of my academic career, I would say, is to convince the ceramic industry to shift to this kind of formation of this kind of green bodies rather than all the stuff that they do where they have substantial amounts of material leak as well as the energy leak. So, and then these are house-made alumina crucibles. So we and we can really very much control the diameter of these things. Again, what I'm trying to convince here, we could do batches of 500 or 5 or 10 through this method. And like with all the other stuff that you have seen, you have to have specialized equipment, you have to have molds. One of the things that we don't have here, we do in order to do the, all these things on a predetermined shape, but we don't need molds. So one of the most important things in ceramics industry, prototyping and such, they had to spend lots of money on the mold, right? And in here, we don't. We really cut down the mold costs. We really cut down all the specialized equipment costs. You just use a single additive at a minimum amount with an advanced ceramic. You hand shape it. You put it into the CNC. You do whatever you would like to do, and then you sinter it. Okay. And we are at the 99.5% of the theoretical density of alumina. If we optimize these things further, there are times we have reached 99.8. So it is like, it's almost the same. Okay, so with magnesium oxide laser machining, this is actually the first processing of magnesium oxide out of a green body through laser machining. I will pass this part. And then, like, what we have done again is the parameterization. We try to figure out what is the what is the laser speed that you should be dealing, what is the power of the laser that you are doing in order to get this highest materials removal without damaging the material. So we have done lots of surface characterization to see, how the material is behaving in the, once interacted with the laser. So we have observed some sintered particles and such. These are also single pass. It is not that we have gone around the same region several times, but these are just simple pass. And these materials are 1 centimeter thick. So you can cut these materials with a CO2 laser 1 centimeter thick and such. And we are also checking, one of the findings that we had was if you use a slow laser speed, you are not doing good to the material. It is going so slowly, it is sintering the edges, but then you have to do rather fast in order to have these cuts on the material. And with laser scaling, we have interesting results. I didn't have the proper collaboration to pursue this, but with laser, you could also, introduce a certain kind of porosity on these ceramic materials. And for the cell growth and such, it might be interesting. But for me, I don't like working with live materials, these things having their own mind. I know she's it is things that have their own minds is not something that I would like to deal with. So, and now we are shifting from oxides to nitrides. That is something that I am extremely excited with, actually, because in here I have presented until now only the monomaterial systems, right? You have the single oxide and then you add a single additive. I would like to underline this multiple times at only like around 1 weight% to have this dough-like behavior. Here we have the SiAlONs and silicon nitrides, like, you know, they are good. But then what people do is they add all these kinds of additional materials in order to improve sintering, in order to improve the mechanical properties and thermal properties and such. So SiAlONs, they have higher performance compared to their monomaterial counterparts. And the idea here is, will we be able to then coagulate this system in the presence of the other materials and then have a dough? And we did. So what we had is just a mixture of all these different types of ceramics in a single batch, and then we managed to get a dough around this. And if you look at this one, in here we are sticking, this is our best formulation, again 78 weight%, with again less than 2 weight% additive in the system. What we have done in this paper is to be submitted soon. Is that what we do is we compare it with a reference sample, and the reference sample is done by powder compacting. So the faculty member who is providing us all these materials is also having his own startup, and they do tools, machining tools out of SiAlON, because it's a very hard material. It is used to cut other materials, and then they produce their stuff with this compacting. And in comparison with them, and then with their compacting, they, you know, before their compacting, they also have, you know, ball milling and such. We also don't have it, again, for resorting to the energy effective systems. And like all hardness values, fracture toughness and density, they're almost the same. So in a sense, again, this is in alignment with our efforts to convince the industry to shift to our way. In order to get similar materials properties which they already do. And of course, we are not going to stop at the ceramics. What about we have the metal doughs, right? So in Cornell, I don't know, I'm not a big fan of Elon Musk, but then if you have been, of course, I do follow him. If you are following up his tweets, he is constantly talking about Inconel. It is one of the metals, one of the alloys that's very hard to process. But of course, like, you know, there is this thing like metals, the ones that are hard to process are the ones you desire most of the time, right? Because if you look at this material selection maps and such, ceramics also, right? You know, the mechanical properties or the thermal properties that are offered by the ceramics, they are kind of unmatched. But then processing of ceramics is very hard compared to metals. Then people usually opt out for suboptimal materials and suboptimal manufacturing processes. So that is what we are trying to change here as well. Like, you know, if we can make it easy for ceramics to be near net shaped, can we really go to the design parameters and pick the best material? Because I also teach material selection and product design. So it hurts me whenever you have to settle for a suboptimal material because of the manufacturing constraints, right? So that is what we are trying to also overcome here with metals, with Inconel. So we prepared also those of Inconel and copper here. This is unpublished results. And then what we do is we do the machining on these things as well. And again, with forces below 10 Newton, compared to what people have to do the processing with Inconel with very hard tools and such. It is as if like we are cutting a paper like this. But the rheological response of these things are very different than the ceramic particles. This is more like kinetic sand, and then this needs to be characterized further. So I don't have much to say on this, but then we managed to shift to metals with the same kind of understanding. So, but powder metallurgy is out there. It's much more common than the, you know, the powder ceramics, let's say, it in parallel with. But then I think we will be able to say a couple of new things for the powder metallurgy. Yes, machining metals. So that part was the ceramics part. And let me shift to surge state part. So I think I will answer the questions in the end. So Anna introduced me as an entrepreneur. And the idea, and what I do as an entrepreneur is we make breasts because like for women, it is very important for keeping the aesthetics of the breast after the removal of the tumor for the cancer treatment and such. And in order for the tumor removal and such, we have like almost 14 different oncoplastic techniques, breast conserving methods that we call them. So this is the idea. So you would like to remove the tumor safely, obviously, but you would like to keep the shape of the breast as nice as possible. So the surveys basically clearly indicate that women who are not happy with their outlook after the surgery, they might forego chemotherapy and radiotherapy. So it is important for surgeons to know all these techniques so that they could be better surgeons. And what we do is these breast models such that people can practice all these oncoplastic techniques, and then they learn how to leave the breast as nice as possible. So we work with almost all general surgery oncoplastic education centers all around the world, actually from Canada, US to India. And this is what I do as an entrepreneur. I think we have the 75% of the market globally. So I'm known as the breast maker in the I introduce myself as the your breast maker. So. And I have a very interesting life. This is what you see is the Dutch consul to Turkey, and like you see me giving him a breast. So and like usually the panel behind the breast is actually pink, but then since to honor our relationship with Holland, Netherlands, we made it orange. So that's like it is a joke. This is actually from a breast cancer awareness campaign that we carried out this year. We put this into the women's laboratories, and there are tumors inside that breast. So the idea is kind of scaring women into getting their annual checkups. So in here, let me remind you, please do get your annual checkups. And men, please also poke women in your life. It could be your mother, sister, girlfriend. And in order to get their annual checkups, like, because early diagnosis, 99.9 survival rate. So that is the idea. And again. And my third hat is this in the investment realm. I really, again, in the beginning of my talk, I told that like, the digital investments, like, I was also, we are all materials people here, right? We really do stuff that we can see either in the microscope or like, in our hands. Like we do tangible stuff, in my opinion. And then the investment scene is usually going after more like digital investments, and then AI more nowadays. But then again, without materials and manufacturing, we won't be able to survive as a humankind, right? So according to me, also in Turkey, the development of a country and prosperity of a company really depends on like, the getting ahead in the materials and manufacturing. So that is what I do in Park Labs. I am having the role of Chief Science Officer, and I am promoting this material science, manufacturing, and robotics companies in order for them to get investment. And I'm really evaluating the technology of all these entrepreneurs, like, the new technologies, and trying to channel money into that kind of works that we hopefully will be beneficial for the humankind. So thank you very much for listening, and let's discuss what we have. Thank you.
Oh, thank you very much, Ozge. It was very interesting. A class of ceramics. I think I was not aware of all different methods and different classes of ceramics. So is there any question?
Yes.
Sorry. About so the green body, after the shape you want, you have to do a sintering.
We do.
And what is the shrinkage?
It is really in line with whatever is reported for alumina, zirconia, magnesium oxide, SiAlON. Because it's a very good question. Thank you, by the way. Because like the amount of polymer that we add inside is very, very small. So we are really getting the theoretical density and then the shrinkage values that are in line with what is out there. So alumina shrinks like 12%.
And well, maybe the problem is not the shrinkage, is the
It's very predictable.
the the shape is preserved after.
It is a reserve. It is a reserve. So we basically do the isotropic, we do the K factors, which I didn't show, but then they show how isotropic is your shrinkage. And we are in all of them, like, below 12, below 2. So shrinkage, isotropic shrinkage, no problem. So it's very homogeneous. And bear with me that it is even not optimized. So we are really doing these things, pushing these things with our hand. So if it was a more automized system, it would even be better. So predictable is the key here, because green body, it is going to shrink. There's nothing we could do. But also, I am very much interested in and this is a collaboration that I am seeking at the moment as well. So ceramics that do not shrink. So because it is also possible with some sintering aids and such, you basically trap the structure and then they don't shrink. Why is it important? Because as you might have realized, these things are like, these doughs, you can actually curve them around surfaces, right? And then there are some other things that, for instance, there are metal rods, and then you would like to have a ceramic around them. So you want to push the ceramic inside a hole and then really dig some metal rods into them. I'm really talking about very small antenna systems and such. But in that case, if you put, for instance, but what people are doing, they're doing slip casting, right? But then once it is sintered, it shrinks. So they have to add more ceramic. And is this something that we can solve? I would like to be just putting this putty inside. If it doesn't shrink, just sintering, then the problem should be solved. So this is something that I will be looking into, the ceramics with no shrinkage. But I'm a polymer person by training. So I really have to collaborate with microstructure on site with the ceramics people. Yes.
So maybe expanding on that point about finding a robotic way to shape the ceramics, because the CNC machining methods that they're sort of take away, they don't take advantage of the fact that you can actually, that it's all soft, right? So they, instead of, as you would normally shape like a pot or something like that, you would shape it with your hands in a shape without actually wasting any material. So I was wondering if you could have tried any other types of...
Can do imprinting. So it is something that I am like, Anna and I, we did soft lithography in our postdocs. So, and then I'm very much aware of what you could do with PDMS, right? I mean, the resolution is amazing. Like you could do 0.5 nanometer resolution with PDMS. This is a thing that I would like to try with ceramics. So, of course, like in order to figure out the resolution of the soft lithography, what we do is a master, right? You push the master and you measure like how small that you can go. I did have a master for these things, but then it sticks to the mold. So when I am doing this, for the very tiny shapes, it really breaks it up. So I think, because what we are doing in terms of the scientific purposes, we are saying we are only adding like, 1 weight% material, right? But it is, again, to explore the ultimate limits of colloidal science. When it comes to the practical version, I think adding some wax and stuff, it will solve this mold problem, and then I will be able to do better imprinting. So it is really it is something we will do, but then we haven't optimized the system yet.
Thank you.
But I think, don't you think like this imprinting will be very interesting? Like also, again, I would like to do this soft lithography concept, because with soft lithography, you can overlay one layer and then you can overlay another layer, right? So a couple of tricks that we always use in soft lithography is also, if you do it in an automated way, you could even like shift the mold a little bit more and then introduce all these kind of feature sizes. So definitely we will, but it's not optimized for it yet. Thank you.
Thank you.
Any other question? I have a question related more on my field, because you were saying that ceramics industry, but you were mentioning different examples of ceramics, and one of them also could be ceramics for implants. And that are very, or should be customized. Have you approached this? I mean, I don't know.
I submitted a pathfinder, which I didn't get.
But with the companies, I don't know if the companies, since they have to customize it, they would be more open, and it's a very small amount that they have to produce.
Actually, in that pathfinder, which again, we didn't get. So the idea was, I am like, again, what is standardization in ceramics, right? If you can really predict the mechanical behavior or the thermal behavior or the cell growth behavior. So what I suggested with a group of people, obviously, but I was the lead PI, is that, like, we can actually gather the data, bone data from all these MRIs and such, density of bones and such, right? So we will get this computerized outlook on the patient. And what we can do is, if this intelligence, let's say, can tell me what the material composition that I would like to optimize for that person, because I could also, as you see, we could do this multiple material systems, right? So with the bone structure, you could make it even very strong, but then you could also intentionally decrease its strength, right? So you could make it more porous and such. So I agree, like, and in here, what I am spearheading is we are generating systems whose behavior is very predictable, because I don't have all this organic matrix and such. We could really control things. So the idea was, again, like, I think it is very possible, which again, I will need a collaboration to do that. But it was the idea. We thought about it, but we didn't get the funding on this. So definitely it's
I
possible.
thought that the companies would be more open, maybe to try.
I agree.
Any other question? I have another silly question. You said that you started with ceramic nanoparticles. Where do you get these ceramic nanoparticles? So
US
it
nano.
US nano?
US nano. So the particles that we use is around 200 nanometers.
Mhm.
And with SiAlONs, we have a collaborator in another city in Turkey, in Eskişehir. So they provide us with the.
And it's easier to obtain. So this is not a problem. You know, to obtain.
These are standard alumina particles or standard magnesia particles, so they are not coated. And actually, I don't want coated particles, because in order for me to do these adsorption studies, I really need to know what is on the surface. So they are not coming from suspension; they are coming in the powder form. And of course, we do some industrial projects, and then in those industrial projects, sometimes they give me 3 micron, 5 micron. It is also possible. So for instance, the Inconel that we are doing is just around 3-5 microns.
Okay.
Related to this, what about the particle shapes? Is
They're all spherical.
spherical, but have you tried like rods or?
Yes. So with the platelets, so
Platelets.
platelets are also possible. So because also, like in this dome formation, which we haven't done this yet, but I bought a pasta maker, but it didn't work out. So in my idea, like, I was going to have this all these platelets in the dough form, and then with the dough form, I will just push it through a pasta maker, so that I will get this maker-like structure. It break up in the pasta maker, because, the right side style, you buy stuff from eBay, and then you do all this kind of do-it-yourself stuff. Yes, it is. But then, so the thickness that I have in these things are not small. So if you ask me to do just 1 millimeter sheet or 500 nanometer sheet, micron sheet, I wouldn't be able to from the dough. What I could do, because again, packing is so good here, so I would like to look into coatings, right? For the ceramic coatings, because like these inks that I have shown you. Go to the ink slide. Come on. Okay. So for the inks, for instance, like if you look at the 1.58%, this could be printed by screen printing. So I could get very thin layers of those things. So for the platelets and such, rather than doing the dough, that is the way. So because with the dough, it is really a dough. But rather we should be exploring the limits of the colloidal science to have things very nicely packed. So if someone is interested in supplying different shapes of colloidal materials, I have a couple of ideas on how to organize them, or like, how to make coatings of them, because there is also lots of industrial interest in order for the coating of the metallic molds, because they against wear and such. So there is also an industrial application for this kind of ideas.
Okay. Any other question? No. So if not, let's thank Ozge again.
Thank you.
She will be around in the afternoon. If anyone wants to talk to her, maybe you can approach us now, and then we organize it. Okay? No, thanks.